So we're in chapter 9 now. And we're going to start in chapter 9, we're going to go to page 9-5. Page 9-5. Because what we're going to emphasize is the two conditions of equilibrium. Page 9-5. The first condition is all the forces have to add up equal to 0. The summation of the forces are equal to 0. Now this sigma stands for the summation. The sum of all the forces have to be equal to 0. And then the second condition is the summation of the torques. The summation of the torques are equal to 0. So that is T, but really the Greek letter is tau, T-A-U, and that's the symbol that we use for torque. All right, so this is torque, and this is forces. Well, a very simple example of this would be a seesaw. And actually, if you have take the lab, you've probably seen the video on the seesaw, because you have a person on one side, maybe a child, over here, sitting down. And on the other side, you have maybe mom or dad sitting on the other side, and they're bouncing out. So what happens is all the forces have to be equal to 0. Well, there's two downward forces. You have the child and you have mom. And the upward force is actually the support in the center. And so you have, now let's say the child is 100 pounds. Let's say mom is 200 pounds. Nope, 50 pounds. Let's not make mom heavy, okay? So mom's gonna be 100 pounds. So that means this upward force right here in the center would have to be equal to 100 plus 50, it's 150 pounds, but they bounce out. Now that's the first condition. The second condition is the torques. Well, what do you mean by the torques though? Well, what happens is this child is applying a force here, certain distance from that center, that causes rotation in that direction. And that direction would be counterclockwise. Now when I say counterclockwise, I always use an abbreviation, counterclockwise, CCW. And mom on the other side, she's going to be producing a rotation this way, and that rotation is going to be clockwise. And the two rotations have to balance out. So summation of the rotations are equal to 0. Now there's two ways to do this problem, so let's just do it the easy way. And the easy way would be to say that this distance right here times this force would be equal to this distance right here times mom's weight. So in this particular case, this torque is equal to R times F. For the child, it's going to be equal to 50 pounds. And let's say this distance is 2 meters, or 2 feet. Let's say 2 feet. And the other side, mom weighs 100 pounds, and her distance would be X. Now, you were all children one time, and so you're probably on a seesaw, so you know exactly what I'm talking about. Your mom would have to stay closer to the center to balance out your weight, and then she would shift her weight so the seesaw could go up and down. So to figure out what the distance is from the center to mom, what you would do is you would divide both sides by 100. So 50 pounds times 2 feet divided by 100 pounds, and you find out this comes out to be 1 foot. And that's a simple example of what we're talking about with regards to static equilibrium. The forces have to actually balance out, and also the torques have to balance out. The rotations have to balance out. Now another problem here, and let's go back to the textbook now. Now let's go back to the end of the chapter, to the problems. And let's look at a problem back here, page about 9-5. 18, I guess. Could be a good problem. And what we have is problem number 9. And problem number 9 is a wheelbarrow. Now, I think everyone's familiar with the wheelbarrow. You have the wheel, like this. And you have a place to put dirt or whatever in here. Like that. And you have handles out here. And you have a person out here trying to move the wheelbarrow. So this person applies an upward force here, and the weight in this problem is concentrated there, where the dirt is in the wheelbarrow. The rotation point is actually right there. So what happens is this person who's pushing up, they're trying to cause this thing to rotate that way. They're trying to get the thing to rotate clockwise. And the dirt would actually cause a rotation going this way, and that would be counterclockwise. And there's 2 torques that have to balance out. So to work this problem out, all we're going to do is say this person's force, let's say the force of the person, times the distance from the wheel out to where the person's acting. And it says here in the problem, I'm going to read the problem for you now. It says that the wheelbarrow, let me just read the problem. A wheelbarrow is an example of a second-class lever. The fulcrum of a 10-kilogram wheelbarrow is located at the wheel. The wheelbarrow holds 25 kilograms of rocks, and the center mass of the wheelbarrow plus rocks is 0.5 meters from the wheel. So that means that this distance right here is 0.5 meters. And this force downward would be 35 kilograms. That's the total, the dirt and everything else, times 9.8 meters per second squared. So the torque here would be 35 times 9.8, 35 times 9.8, times the distance, which is 0.5 meters. And the other side, you have the person, and we have to know what this distance is. Well, read the problem now. I'm going to read the problem again. We'll always read these things at least twice. It says the fulcrum of the 10-kilogram wheelbarrow is located at the wheel. The wheelbarrow holds 25 kilograms of rocks, and the center mass of the wheelbarrow plus the rocks is 0.5 meters from the wheel. What upward force must the person exert at the end of the handles that are 3 meters from the wheel? So we know this distance right here is going to be 3 meters from the wheel, like that. And so it's going to be 3 meters right here. So the the force the person exerts is going to be 35 times 9.8 meters per second squared times 0.5 meters divided by 3 meters. And assuming I did not make any mistakes, this is going to come out to be about 57 newtons, and that's the answer I have in the book. About 57.2 newtons. And we can shut it off.